Homework 4. In the first problem, I want to factor a couple polynomials over the finite field fp. So part A, we're looking at x to the p minus 2 power. So what I would suggest here is use a fact we learned, a couple facts. There's Fermat's little theorem that says 2 to the p is congruent to 2 mod p. And there's another fact we learned that said if you raise a binomial to a pth power, mod p, or working in the finite field fp, what does this equal? Well, this is just x to the p plus y to the p. All of the other terms are divisible by p, and so they just vanish in fp. So use these two facts and give me a complete factorization of x to the p minus 2 into linear factors. So I want a complete factorization. And then on part B, you should recognize the p minus 1 over 2 power reminds us of the Euler criterion. So just find all of the zeros using the Euler criterion. Right? And so you should be able to characterize precisely what these p minus 1 over 2 zeros are and write a complete factorization. Okay, in problem 2 we're finding square roots of numbers mod p. So in case 1, p is a prime congruent to 3 mod 4. And I want to solve this congruence, x squared congruent to a mod p. And I claim all I need to do is just plug in this value. So this is just a plug-in problem. Take this number, plug it in, square it, and you want to show it's congruent to a mod p. So what would that mean? That would mean that a to the 2k plus 2 should be congruent to a. And now a is a quadratic residue, so it's not divisible by p, and so if I cancel that on both sides, I'm just kind of working backwards here. Plugging this in, and I want to show that this is going to be true. Well, that's equivalent to this, and this is equivalent to what? And now use the fact that a is a quadratic residue, and think about what the Euler criterion has to say. Or in part B, it's very similar in nature. So this time p is congruent to 5 mod 8. And I want to show that these values would satisfy this. So again, think of the Euler criterion. So if a is a quadratic residue, what does that mean? That means a to the p minus 1 over 2 power is congruent to what? Mod p. And then we have another fact that we've seen. You can use x squared congruent to 1 mod p. Means that x is congruent to plus or minus 1, so feel free to use this fact. Another fact that would be useful in this problem is when is 2 a quadratic residue? So if p is congruent to 5 mod 8, then when we studied the section on Gauss's lemma, we established when 2 was a quadratic residue. So what does this say 2 is equal to? The Legendre symbol 2 over p, think about that. And of course the Legendre symbol means 2 to the p minus 1 over 2 power. So this is congruent to 2 over p, which from the Gauss lemma we established was equal to plus 1 in certain cases and negative 1 in other cases. All right, so you're going to use that fact here, and I think you can put this together and just establish these things. Problem 3. So I want to count the number of solutions, so there's 12 solutions. So if I let n of 2 cubed be the number of solutions mod 2 cubed, and then I'll let n 7 to the 4th be the number of solutions mod 7 to the 4th, and then the number of solutions mod m is just the product of these two numbers. So let's focus on mod 2 cubed first. So take this congruence, mod 8, and find all the solutions. Well, there's two cases to think of. Case 1, x is even. And if x is even, I claim you can solve that congruence very readily. And we're counting how many distinct values mod 8 are there. So find all the distinct values mod 8 when x is even. And then case 2, x is odd. So when x is odd, you're going to use the fact that x squared would then be congruent to what? 1 squared, 3 squared, 5 squared, they're all 1 mod 8. So you can simplify this equation using this fact. So what does x to the 495 become? What does x to the 24 become? And so you can very readily find all of the odd solutions to this congruence. So you don't need to use any of the lifting concepts for this one. And then we have to go to mod 7 to the 4th power. And again, we can think of two cases. One is a case where 7 is a divisor of x. And you can very quickly determine whether you have any solutions mod 7 to the 4th in that case. In case 2, 7 is not a divisor of x. And when 7 is not a divisor of x, then x to the 6th power is congruent to 1 mod 7. And so this congruence greatly simplifies when we're looking at it mod 7 equals what? Mod 7. So on this problem, we're going to do the lifting process. We're going to start by solving it mod 7, by simplifying this equation using this fact. And then once you find all of the mod 7 solutions, so first find all mod 7 solutions. And then in step 2, you're going to lift those. Lift to mod 7 to the 4th. Now when I say you're going to do this, I'm not asking you to find the solutions here. I want you to count the number of solutions. So you're just going to have to see, are these singular solutions or non-singular solutions, and do they lift? And then once you've calculated these two numbers, you just take the product. N of 2 cubed, n of 7 to the 4th. Problem 4 is just a standard lifting problem. So we first of all find all of the solutions mod 31, and then in part B we're going to find solutions mod 31 squared. So I've given you that one solution is 3, 27, 30, 31. And so now just use long division factor this out, and you should come up with a quadratic up here. Just standard long division. Keep in mind that you're working in the mod 31 field, etc., etc. So you should come up with a factorization x cubed plus x plus 1 equals x minus 3 times a quadratic. And then you need to find the zeros of the quadratic, and you can just use the quadratic formula. Find zeros. Keep in mind the square root means we're doing a square root mod 31 to find the in the application of the quadratic formula. And then part B, we're just doing a standard lifting. So once you have the two solutions in part A, so one of the solutions is non-singular, and that'll lift to a unique value, mod 31 squared. And the other one is a singular solution, so this is the mod 31 level. And that has two possibilities. It'll either lift to 31 distinct solutions, or it'll have no lifting. And you'll have to figure out which one of these two. And in both cases, you just use the lifting congruence. So the lifting congruence says you take the derivative of the 0, evaluated at the 0, whatever these 2 points you found in part A, times t should be congruent to minus f of a over p mod p. You're looking at this linear congruence, and we're just calculating to see if we have any solutions here. Problem 5. Let p and q be primes. P is a divisor of a to the q minus 1, but p does not divide a minus 1. Prove that p must be congruent to 1 mod q. Okay, so what type of hints should I give you here? Let's just look for the order of a mod p. That may be enough. So what could it possibly equal? So this, turn that into a congruence. Mod what? That gives you some information about the order. Now, p and q are primes. And then we have a theorem that says that if you're in a group, in a finite group, what property does the order of an element always have? Well, the theorem doesn't ask a question. It's going to answer this question. So in a finite group, what property does the order of any element have? So put those facts together. Problem 6. Show that for any positive integers a and q, this GCD equals this GCD. And this is just Euclidean algorithm. So just think of performing the Euclidean algorithm on these two numbers, and just write out this number in expanded form like this. A plus 1. Right? That's what you get when you divide these two numbers or you divide two polynomials. You're thinking of getting that. And now just divide this integer, this big number, by that and find the remainder. So you'll have r, a minus 1, where this is the remainder in the division. And going and dividing the two numbers. And just carry it out using long division or synthetic division, whatever you like. So you have this number divided by a minus 1. Deduce from part A that if q is a prime and a is not congruent to 1 mod q, then this GCD equals 1. Well, I don't think I need to do anything. So here's the GCD. Q is a prime. What can that GCD equal? Part C, we're going to try to prove there's infinitely many primes congruent to 1 mod q, where q is just an arbitrary prime. So this is a vast generalization of what we've done before to show there's infinitely many primes. I think we had another problem where we were doing infinitely many primes congruent to negative 1 mod 4. And they all have a similar flavor. So you do a proof by contradiction. This time we are concocting this special number in order to come up with a new prime not in our current list. So the hint is consider a prime divisor of a to the q minus 1 over a minus 1 and then use problem 5. So think of this as 4 steps. So in step 1, if p is a prime divisor, p is a prime, dividing a to the q minus 1 over a minus 1, show that that implies p is a divisor of a to the q minus 1. That's very trivial. 2, show a is not, or p is not a divisor of a minus 1. Using part B of this problem. Step 3, now let's use problem 5 to show p is congruent to 1 mod q. And then finally, I want to show that p is distinct from all these. P doesn't equal P1 through Pk, and thus we are getting a contradiction. We're getting a new prime congruent to 1 mod q. So try those 4 steps. Problem 7. Use Gauss's lemma to calculate the value of 3 over p, the Legendre symbol 3 over p. So in the lecture notes we did 2 over p, and we proved this fact here, that the value nu coming up in Gauss's lemma is the sum of these greatest integer differences. So in this problem, I just want you to use this formula we derived in the proof of when we were doing quadratic reciprocity to directly calculate 3 over p. And is there anything more you need to know? So first of all, find b. So you just plug in a equals 3, and you get a value for b here. It's not going to be a very big value. And what do? Well, then you just, it's going to be very similar to what we did for 2 over p. So if you need a little more hint, just look at what we did to how we calculated 2 over p. only this time you're going to say, okay, let's let P be of this form, where you have some number plus 12t. So you have some reduced residue plus 12t, where r is going to be some number relatively prime to 12. It could be 1, 5, 7, or 11. And calculate this value. Let's see, problem 8. Use quadratic reciprocity to evaluate 5p for all primes p. And then note how it only depends on the value of p mod 20. So, well, 5 is congruent to 1 mod. So 5p, we can just flip it. And then all you're left to do is find what are the perfect squares mod 5. And then in part B, if p is an odd prime, n is a positive integer, with p dividing this, prove that the ones digit, just turn this into a congruence. Think of it like that. And so if we're given that this is solvable, right, that n squared is congruent to 5 mod p, that means that 5p equals what? And now use part A. Because in part A you've characterized what primes will make this equal to the number you're looking for here. Problem 4, we have a couple examples in the lecture notes. You can just follow the examples in the lecture notes on this. So you use quadratic reciprocity, and you can work with Jacobi symbols, so you don't even need to worry about whether we have primes in the top and bottom or not. And then problem 10, determine all integers that can be represented as a difference of two squares. So let's just make a list of all of the perfect squares. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then they keep getting more and more spread out. 25. Etc., etc. And just kind of look at this and see what numbers can you get. So start by just doing this with a little experimentation. So I can get 1, and then this difference, and this difference, and I go along like that, and I can see, oh, there's a nice pattern for differences of consecutive squares. And then you play around with double hops. So maybe I'll go from 0 to 4. That difference is 4. Or from 1 to 9. That difference is 8. From 4 to 16. And so on. And you'll get another set of numbers. And then you say, well, maybe I'll do a triple hop. I'll go from 0 to 9, or from 1 to 16, etc., etc. So you'll come up with lots of numbers that can be expressed as a difference of two squares just by doing some trial and error. And then after you've done that, show that the values you're coming up with in trial and error are really the only values that you could possibly get as a sum of, as a difference of two squares, so that you have exhausted all possibilities. By asking yourself if x squared minus y squared is equal to A, what does this tell us A must be congruent to mod 4?